Let's go to next talk. Holger, are you ready?
Sure.
Okay,
Can you hear me?
okay. So I'd like to introduce our colleague from Germany, Holger Schlingloff. Will present his talk about interactive talk. Yeah, you're welcome.
Sure. So this is what I want to show you. Thank you, and thank you, Alexander, for the invitation. And it's my pleasure to be here. Again, like my previous speaker, I want to introduce myself. I'm professor at Humboldt University, and my subject is specification, verification, and testing of embedded software. And I'm also employed at Fraunhofer FOKUS, which is the largest computational science institute of Fraunhofer, located in Berlin. And we're doing applied work with industrial companies on the verification, on practical verification. And so it will be a somewhat relaxed talk because I will talk on a little bit on philosophical things and only quickly mention technology and formulas and maybe skip over them. So this is the structure of my talk. The topic is formal methods for reliable autonomous systems. So the focus is on autonomy. So I will firstly talk about autonomy, what it is, what I mean by reliability and formal methods, and then talk a little bit about challenges and approaches, specification, validation, and engineering of autonomous systems, and then the main part will be examples like trains, trader agents, transport robots, and so on, and then tell you what we have done or what you could do with formal methods here in simulation, model checking, online monitoring. And then I will quickly conclude my talk. So the purpose of this talk is to get you interested in a recent open access paper, which has been published a few months ago. It's called Towards a Framework for Certification of Reliable Autonomous Systems. And it's quite lengthy. It's like 60 pages or so, but you can click on it, and maybe I could post if there's a chat. No, it's not accessible here. I can post the link in the chat after the talk. Yeah, so talking about autonomous system, the question is, what do we mean by an autonomous system? I always look at the origin of words when explaining to my students. Of course, autonomy comes from autos, meaning self, and nomos, meaning ruled. So an autonomous system is a self-ruled system. And Wikipedia also defines autonomy as the capacity of a rational individual to make an informed, uncoerced decision. And it further goes on that this concept is referenced in discussions about free will, fatalism, determinism, and agency. And so there is a large body of literature in philosophy about independence of control. But of course, this concept becomes more and more important also in engineering. So autonomy does not only refer to human societies, but also to artificial or engineered systems. And an autonomous system in engineering is a system which can perform desired tasks in unstructured environments without continuous human guidance. Again, definition from Wikipedia. I mean, a system is autonomous if it can make its own decisions and act on them without external supervision and control, and in particular, without human supervision and control. So why is this concept important, and why is it of growing importance? Well, if you look at the history of engineering and technology, a hammer or a weaving machine or a bicycle is operated by a human, and it does not really act. The systems do not act by themselves. So the human is capable to control all of the system's operations. It has to make sure that she follows the rules and also adopts ethical principles or meta reasoning. So the human has full control and also full responsibility. But of course, as systems get more sophisticated, we have, let's say, cars or trucks or complex machinery, the human delegates the control of some basic tasks. So a car, you do not have to provide the power, but the power is provided by a motor. And so the human, in some sense, controls some of the system's operations, but still driving a car, you're responsible for following the rules, and also in exceptional cases, how to behave, it's your responsibility. Well, systems become more and more complex, and now we are in a state where we have systems which are augmented by human beings. So what we have planes and assisted cars and robots, where the human delegates not only the control of the system's operations, but also the following of the rules. For example, that a car stays in the lane, or that it recognizes a stop sign that is in the near future. Still, as a human, you're responsible for adopting ethical principles and following meta rules. The responsibility still at the current state of the art is mostly with the human operator. But this will be changing in the near future if we are talking about systems which are solely controlled by computers. So the systems which are fully autonomous also in unusual situations. So they must be capable not only to follow rules, but also to handle in exceptional situations, handle reasonably. So the responsibility, well, where is the responsibility? This is a public debate at the moment. Is it with the operator? Is it with the producer? Is it with the engineer? So responsibility somehow seems to dissolve. And of course, it's also maybe with the assessors or the authorities who admit such systems. And therefore, in this paper, we are dealing with the question of how can this, from an engineering or scientific viewpoint, how can this interaction with assessors and people in the authorities be organized? So the different domains, let's say trains, planes, automobiles, have come up with a classification of autonomy. And one which is given here is from the Society of Automotive Engineers, taxonomy and definition for terms related to driving automation for road vehicles. So the level 0 would be no autonomy. Level 1 would be low autonomy, where you have straightforward but non-trivial tasks being done by the system. Then you have assistance systems. That is what is currently on the road, like driver assistance systems or parking assistant. So the operator assistant is assisted by automated systems, but remains in control. Then you have partial autonomy, level 3, where the system takes full control of the system. The automation system takes full control of the technical system, but the operator must remain engaged. That is like a steering assistant, which you find in, let's say, sophisticated cars nowadays. It will keep on the lane, but of course it's your responsibility. Then you have conditional autonomy, where the system, the controller has full control of the operation during specified tasks. For example, you can read a newspaper while driving, and the system will alert you. And then the next step would be high autonomy, where the system is capable of performing all planned functions under certain circumstances. For example, you There have been research cars driving all through Germany from Hamburg to Munich on the highway. So they can do this all automatically, and the operator can leave the system alone in this circumstances. So it's possible, feasible, but it's not yet admitted on the road. And full autonomy, level 6, would be that the system can perform all its intended tasks on its own, and no human intervention is required at any time. So you get in the car from in front of your door, and you leave the car at the destination, and you don't have to touch anything in the control. That is still a future ahead, but at least in automated driving, people are talking that we will reach this step within the next 10-15 years. So what does it mean for a system to be reliable? Well, of course, if we look in the dictionary, we see that reliable means suitable or fit to be relied on. So that means that a service or function is available when needed. Yeah, and reliability often is associated with the notion of a certification. So in order to be reliable, we want a system to be certified. And of course, what does a certification authority look for? Well, it looks for the correctness. Correctness means conformity to a specification. However, the specification often is not available. So we want to make a software system reliable in the sense that it makes good decisions in all situations. What is a good decision? Well, usually a good decision would be to follow given rules, choosing to stop at a red traffic light or driving on the right side of the road. However, there might be a roadblock ahead, and then there's an exceptional circumstance where you have to cross the lane and go onto the other lane and see whether there's no car coming. And so such rare situations, a good decision would be not to follow the rules, but to follow the meta rules, which allow you to break the rules. And often these meta rules are not explicitly spelled out, and they are in the back of the mind. Of course, if there's a roadblock in front of you and you need to go on, of course you have to cross the road and go onto the other direction. Yeah. So the question is how to qualify such autonomous systems, and in particular how to regulate what do we need to specify here, how to verify reliable behavior. And of course, there the question is, what are the usual sources for regulation? What are the standards? Which are the laws? Which are the checks and certificates which you can obtain? And we looked at what is available, and we found we sketched this on 2 dimensions. So the scope of autonomy, what systems can be doing in terms of autonomy, and what is the amount of available regulation. So we looked at that for certain examples, simple examples like a robot vacuum cleaner, but also more sophisticated examples like a self-driving car, which has a high level of autonomy. And we found that for the highly autonomous systems, there is little available which tells you how to follow unformulated specification and so on. So full autonomy means we do not delegate rule following, but also unusual situations and ethical principles. And the question is, what is needed to qualify such behavior? And when would we as a society allow such systems to be deployed? What would be reasonable here to allow such systems to be on the road or on the street or out in public, or for an autonomous trading system on the market? So here's an overview. If you look at the paper, you can find an overview of available standards. And what you can see is that the standards, also the more recent ones, do not really look at these topics which I just mentioned. There are some initiatives at the moment. IEEE, for example, has a global initiative on ethics of autonomous and intelligent systems, where legal or ethical requirements are given in natural language. And so it has, for example, a standard for ethically driven nudging for robotic, intelligent, and autonomous system. However, what we see is that in these systems, potential hazards are uncertain and changing, and it is not really clear how to go about. And the decision-making process in autonomous systems generally is intransparent. What we propose, or what I strongly follow, is to apply formal methods here. And I have been working in formal methods now for quite a number of years. There is a recent book which is upcoming. It should be out, let's say, in September or October, where we give an overview of formal methods for software engineering with 4 co-authors. And we define a formal method to comprise of syntax, semantics, and a method for dealing with formal objects in order to establish or assess the correctness of systems. And of course, formal methods come in many flavors: textual or graphical modeling languages with different types of semantics, operational, denotational, axiomatic semantics. And there are very many methods being proposed: theorem proving, model checking, static analysis, runtime verification, testing, and so on. You can find much more in this book, but you can also find some classification of formal methods in this article, which I referred to and which I'm reporting about today. So there are many dimensions according to which formal methods can be classified. First of all, you can classify them according to what syntax is being used, what semantics is being used, which method is available. But then other dimensions are the application range, the technology which is underlying the properties which are being formulated or which you can verify or look at. And then, of course, the maturity and applicability for different domains. And in our paper, we come up with this classification here, where we say we have a formal or semi-formal, and we have exhaustive or non-exhaustive, and then static or dynamic. And you can see that theorem proving, for example, is classified as being formal and exhaustive, whereas, for example, runtime verification is somewhat between, is more on the semi-formal level and on the dynamic side. Yeah. So this is a classification. And of course, we can also order this as a tree of formal methods, where we say we have explicit or implicit modeling. Explicit modeling is in model checking, where you have a formula and a model, and implicit is in theorem proving. Is there a question? No. Implicit modeling. There's somebody an echo. Implicit modeling means that the property is the model is coded with the property, and then you have different stages when it's being applied: static versus dynamic, or design time versus runtime. So, for example, runtime, of course, is a runtime verification. Of course, is a runtime method, and then we have different technologies. Like binary decision diagrams, or bounded model checking, or property-directed reachability, or SAT solving, or satisfiability modular theories. And you can find, we categorize the different methods in this tree according to its what its input, what its output of the method, and what are the strengths and weaknesses, and where is it applicable. So if you want a crash survey of formal methods for autonomous systems, please go and look in this article. It gives you a short introduction. So, but it's not only stock taking the article, it's also elaborating challenges and proposing new approaches. So what we think are the main challenges is one, which I mentioned, are the requirements and specification, the problem with requirements and specification. So how do we capture exactly how we want the system to behave, what we expect it to achieve, and overcome the difficulties which arise when human level rules do not already exist. So this implicit knowledge of what to do in exceptional situations. And we propose to discuss this with regulators to give formal description of what is needed, and we give a process which can be used to identify requirements from the regulators here. And then, of course, there is a verification and validation issue. What are the appropriate technologies in order to verify and validate? So we provide a wide range of technologies across different levels that can be used. We review, as I told you, the existing techniques and their applicability. I want to comment on that furthermore. But of course, we are also identified architectural or engineering issues. That is, how can we construct an autonomous system in such a way that it's amenable to inspection, analysis, and regulatory approval? And in this category, we provide a reference framework, which consists of three layers of autonomy, of decision-making that separates the different issues. So here are the key ideas of our process for identifying requirements. We have to consider the human context in order to identify requirements like licensing. How is it usually done with humans? What are the assumed human capabilities? What are the necessary laws and regulations? And what are the interfaces? And then we propose to consider how to assess requirements for an autonomous system. For example, the behavior in different scenarios rather than exam-based. So if you want to drive a car, you have to pass a driver's license. And the question here is, what would be a driver's license for an autonomous car? So we detail this process in various steps. So there's a licensing step, there is the capability step, there's a legal regulation step, and there's the interface step. And you can read about that in our paper, how the different steps are about to be done here. About the architecture, we propose to layer the decision-making in 3 layers, the reactions layers, the rules layers, and the principles layers. We frame that by what is the environment, how is the environment supposed to, or what do we know about the environment, and what are expectations of these layers to handle. Well, of course, the reactions layers, we have a model of the expected environment. For example, how to steer a car on the road. If you turn the steering wheel, how will the car behave? What will be the trajectory? And so you have you expect from this layer of decision making that, for example, if the wheels turn in that direction, then the car will move accordingly. So that is all mathematical, well understood, and in particular, it's what I'm just teaching to my students, how to do that, how to develop such reactions layer. But of course, there is a layer on top of that, which is the rules layer, where we have set out all the rules of let's say, following traffic laws and so on. So we have anticipated scenarios, and we want the layer to follow the rules and the regulations in this term. And then, of course, there is the principles layer, which should come into play when something unexpected comes about. So there's unexpected or unanticipatable behavior of the environment, and we need general principles and priorities which the system has to follow in this respect. Yeah? So I will tell you a little bit more about this, how this is implemented or how this can be implemented shorter. So now I come to the examples part. In the paper, which I referenced, we consider several representative examples. And for each of these examples, which were given in the table below before, we consider where the example is positioned with respect to the layers in our three-layer framework. What is the level of current and future autonomy? How safety critical is the example? And what are the available regulations in the aspect of autonomy? And what are suitable verification, validation, and analysis techniques? Yeah, so this is how these examples part in our paper is structured. And an example would be a home assistant robot. Some years ago, there was a nice movie called Robot and Frank. The picture you see here is from this movie. It's a robot assisting elderly people. And in this particular case, this elderly person is has been a thief. And so the robot also assists him in stealing things from a warehouse, which of course it has this principles layer where it should follow the rules of society, but above that is the rule of helping this owner. And so human well-being can pose ethical issues, which is a nice perspective in this movie. It ends that the police, of course, finds out about this illegal activities, and then the robot decides on its own to erase its complete memory, because it has, of course, stored all history of what it did. And so it, in a sense, commits suicide in order to assist the human in not going to jail. And that is a somewhat neat clue in the movie. With such an example, what is the level of autonomy? Of course, here's a trade-off between trust and following rules. Of course, the owner should trust the assistant robot, but of course, the robot should follow rules, and there are rules of society and rules of individuals, and the question is which are more important here. Of course, the system is highly safety critical because it is also supposed to call medical help if it is needed. It's also supposed to help like bringing medication and so on. So if it makes mistakes, then this could be a disaster. And of course, for such a system, it's not yet existent. There's little regulation. So it's neither an industrial robotic system nor is a medical device. So there is no domain yet available for such a system. And of course, what would be suitable to verify, validate, or analyze such a robot is ongoing work. Of course, runtime verification, because it's a learning system, so the behavior changes at runtime, so we need techniques here to validate and assess systems also during runtime. And what plays a role here is also privacy. I told you that the robot erases its own memory and its own personality in order to protect the human owner. So also privacy is a major topic here. However, for the rest of it, there are lots of other examples in the paper, like I told you, a vacuum cleaner, an autonomous trading system on Wall Street, a driverless train where we are very active in developing that, unmanned aerial vehicles, drones, self-flying drones, self-driving cars, and so on. However, before diving more into these, well, I did some work on driverless trains. With kids, I develop soccer robots, which could be compared to vacuum cleaners. But I'm not developing home assistant robots. I would rather tell you about some work which we did with a company in Adlershof, in Berlin Adlershof, which is on autonomous transport robots. So this has been ongoing work for the last, let's say, 5 to 10 years. So these are driverless transport vehicles which serve and load and unload production machines with weights of to 20 to 200 kilos. Let's see whether there's a small movie. Let's see whether this works. I hear that Zoom is quite bad in transmitting video files, but maybe you can see something here, how the system loads and then drives around the factory and delivering these goods to the various machines. Can you see that?
Yes, it's visible.
Okay, good. So usually such a fleet has about 5 to 20 robots, so quite a feasible number. And of course, these systems have a historical development. So the first generation was that they were on rails or following a certain line. Then the second generation is that they moved on dedicated roads where no human was allowed. So it was separated by a special color on the ground. And now the third generation is it's moving freely in the factory with humans, interacting with humans, and of course all kinds of problems come in this interaction of humans and robots. So, for example, I was in a factory where these robots were moving around, and along comes a robot and humans talking and chatting and smoking a cigarette. And I respectfully stepped aside. But of course, the workers who deal with every day with these robots, they just don't go away. The robot has to circumvent the human. It's not the task of the human to step out of the way of the robot. So my vision is that the servicing of machines will be completely done by robots, also in exceptional cases, if there are roadblocks or if there are damaged robots and so on, and that humans are only for the supervision of these machines. So how did we implement the 3 layers in these robots? For the reactions layer, of course, the main problem is the localization. How does a robot localize where it is on such a map? So there is a built-in laser scanner. Here you see a picture of it. And this laser scanner serves both the safety. So if there's an obstacle within a dedicated range, let's say 1 or 2 meters of the robot, then it just stops. And it also, the laser scanner also can localize the robot on the map. So the robot has a map of the factory, and then it has a picture taken by the laser scanner, and that it makes it puts these atop and says where's the maximum likelihood where I am at the moment. For the rules layer, of course, we have route planning algorithms. The rules are, for example, bring load A from machine, bring a certain load from machine A to machine B. And so there's basically a Dijkstra shortest path algorithm for such route planning. And for collision avoidance, this shortest path algorithm is being modified. And so there's a dynamic window algorithm, it's called. But of course, then we have the layer above the route planning, which is the principles layer, and that deals with how to schedule a job. And currently, there is a central server which does a FIFO scheduling. The jobs are distributed. The next job is distributed to the first robot, which is free, which is idle. And of course, that has lots of problems because it does not respect all the exceptional circumstances and all this ethical or principles layer. Robots may have hardware failures. The roads may be blocked permanently. Machines may be out of order or moved and so on. The wireless communication may be distorted. And last not least, it is that the server as a single point of failure may also break down. And so there are, what we did design is we did design the collaborative control of this. So we wanted to have the robot own responsibility for the behavior, also in exceptional circumstances. So we designed some auction-based mechanism where the robots bid for jobs. So the jobs are posted by the central server, and all the available robots can apply for this job. So they have some virtual money which they distribute, and their intention is to earn as much money as possible for their employer. And if they are idle, then they lose money, and if they complete a job, they earn money. But they can also auction, so they can spend money to buy a new job. And by this, we get more flexibility and robustness. We get a higher throughput. We get better scalability and more security. We have this ethical layer implemented. Could be discussed in how far being commercial is being ethical, but that's another story. So the question is now, how do we verify or validate or analyze this behavior? And of course, one part is that we have a simulation, and we have various variants of these centralized job assessment strategies and also the decentralized. And then we made a simulation. Here you can see it. Where the robots are in the factory floor. In fact, this is a map of an actual factory floor and actual machines. And we have a number of robots around here, and we have a number of defined jobs. And then we have the job distribution, and we can measure how long it takes to satisfy all the jobs. Yeah? So this is a simulation approach. And we can get some results of this simulation, but of course, that is only an average result. We found that the efficiency highly depends on the scenario. How many robots, how many machines, how many jobs, how long are the jobs, and so on. So we think that maybe an optimal strategy also needs to be adaptive and learn. Currently, we have only strategies which are fixed from before. And of course, such a simulation does not allow you to rigorously analyze properties. It only gives average results. So there are other properties like temporal properties, no deadlock, safety, liveness, responsiveness, best or worst case timing, throughput, utilization rate, fault tolerance, roadblocks, failures, and so on, and even flexibility properties. How do we deal with new robots in the team or alternative floor plans? And of course, there are also strategic properties. What do you do if there are, let's say, traitor robots or traitors trying to enter the team and bring the system down, and so on? So these are properties which are worth analyzing and investigating. And of course, we can resort to well-known techniques, for example, linear temporal logic. so we can formulate the model, the scenario in a LTL setting, and then we can use model checker or theorem prover to verify such an attempt. However, due to the fact that this is a highly spatially dependent system, the model quickly becomes very large, and then temporal logic is doomed to the state explosion problem, so you cannot get too far. We did some experiments also with timing verification by UPPAAL, but it turns out that the abstraction is so coarse that the results are not really useful. So we need some, so here are properties with UPPAAL, for example, that no deadlocks occur, which can be formulated as a temporal logic formula, that deadlock means that all jobs are finished, or that all jobs are finished within this given time, and so on. This is all standard technique, but as I said, it can go only so far, and not to a level of detail where it would be really useful. So we used, for non-functional properties, we used probabilistic model checking. So for example, performance evaluation is a non-functional property, and it considers also the fact that roads may be blocked by human workers, and robots may need to wait for other robots. For example, here in this scenario, you have a small pathway where the robots need to pass. And so if there are a number of robots on one side and they need to get back to this machine, then there may be a traffic jam here. Or this is also a picture from a factory where this is employed, where the robots can use such a lift to move between different floors. So this robot lift is already in use. And so here we used, for this probabilistic model checking, PRISM is a standard model checker, but we also used an extension of UPPAAL, SMC, for stochastic timed automata. And we need, the model itself consists of 3 submodels. One, the model of the system, meaning the robots and the job scheduling. Then the model of the assembly stations, and then the resource model. And by separating these models, it is a little bit more scalable than the temporal logic approach. And here are some properties. For example, performance properties. I promised you not too many formulas, but here are some at least. The property is smaller than a threshold. Now, the property, the probability that the response time within the first 1,000 time units shall be less than 450 time units in 80% of all the requests. And so this is a way to formulate that the time difference between the time when a job is created and the time when a robot finishes the job is reasonably low. Yeah? So the response time is good in some sense, or the throughput can be specified in this temporal logic. Well, I'm not going into details there. If you're interested, please drop me a note. There are papers where this is written down in detail. And of course, there are also some results which we can get, and sometimes also surprising results, which also surprised us. So that, for example, in this situation, you have more robots dealing worse behavior. Well, this is somewhat to be expected if there's such a traffic jam. But then there's also this case where we have more robots than being more successful with a certain required response time. So you get really, by the probabilistic verification, some surprising results which you could not get by just estimating or simulating, because it's of course a complete technique going all possibilities. But of course, we also want to observe the system during runtime. This is what we mentioned before. In particular, we need to do that if the system becomes learning and adaptive. So we have not yet, in this transport robot use case, we do not yet have a learning approach. So we have this auction-based approach, but it's not learning. So if we have a dynamically adapting or changing system, we need to do online monitoring, and we observe the system's traces to detect deviating behavior. We give the specification by a logical formula. We have a defined metric temporal logic. We also experimented with other approaches where we have a diagram. One approach is, in one paper, I sketch how life sequence charts can be adapted for this approach, or it could be even code, Python scripts, surveying such a system. And we will do that. There's an upcoming project where we will implement that, where we supervise the system with a script, and then we evaluate this, the results of the script with respect to a formula. So of course, this is not model checking, it's not simulation, and it's also not testing, because we have no artificial stimulation. We just observe the system. But of course, we want to get some meaningful results out of this. And currently, we have deployments where there is still this centralized control. And that is good, because the centralized control is logging almost everything. So we have a very huge number of huge event logs, gigabytes of event logs, millions of events. And we analyzed these logs and found out that the vast majority, of course, of the log files is position messages of the robots. I am here, I am here. But there's also a messages about order status and docking. I successfully attached at machine X, or I'm unable to localize myself. Can you please help me where I should be? And generally messages about the status. I'm out of order, or I need help, or whatever. And what can we do? Well, we can define a specific temporal logic, which is an extension of metric temporal logic with graded modalities, where we define the semantics. And for example, this property means always, whenever there's a request, it will be finished within 5 time units. That's responsiveness and so on. But of course, we would like to find or anticipate deviations of such properties before they occur. Yeah. So what we see is that order processing this response can take quite some time. And of course, if you look at the time which it took to complete an order, you see that the average is here quite fast, a few seconds. But there's also like more than 6,000 seconds for the longest job. And that is, of course, a catastrophe. So you would like to know what's about to happen here before it happens. Yeah, and you want to do something about it. And so we defined robust semantics for this logic, which can predict, and the truth value of a formula is the distance to a deadline. So with these formulas, we can predict that problems are going to occur. And we can take measures. That is an example of rule breaking in some sense. I told you on the ethical layer, we need some rule breaking. And here we are about to implement something like this. Coming back to the original paper and towards the end of my talk, in the paper on autonomous systems, we identify some challenges on the research side, on the engineering side, and on the regulatory side. And I'm not going to tell you about all the challenges, but also focus on this research part. So I told you that we are currently investigating how to specify, perform, and verify principle-based reasoning on this ethical layer. The other thing we are currently looking at is how to handle evolving knowledge and machine learning. And this is in the railway domain, where we want to find out how to certify AI systems in autonomous railway operation. Of course, complexity and scalability is an important issue. I told you if the model strongly depends on spatial aspects, it tends to grow very fast. So there's still this quest of how to overcome this problem. And another topic I'm investigating is automatic synthesis of correct systems. If you have a specification in some temporal logic language, can you come up with a controller which automatically satisfies such a specification? Well, on the rules and the reactions layer, on the reaction layer, this has been investigated for quite some time. On the rules layer, it seems to be a very hard problem. On the third layer, on the upper layer, it is that this seems to be in some sense also feasible, because the rules may be, the ethical principles may be not so complex. And of course, we need to find out how to explain systems for regulators in order to come up with some guidelines on how to develop the technology. So this brings me to my conclusion. We talked about formal methods for reliable autonomous systems. I told you about challenges in specification, validation, and engineering. Hopefully, as a takeaway message, you remember the 3 layers architecture for for the design and validation of such systems. I gave you several examples. In particular, I talked more extensively on the case study of autonomous transport robots. There's a bunch of papers which I can send you if you're interested. Different verification goals need different techniques for verification. So I gave you some properties: timing, flexibility, performance, and security. I did not talk too much about security, but there are papers on it, and the different techniques which we used to verify such goals. However, I also made clear that there are many questions which are yet unanswered, and so there's a lot of research potential. I understand that this is a conference for young researchers, so I would be more than happy if you approach me and I tell you more about the many questions which can be investigated and where you can write a PhD or other thesis. And so therefore I would like to thank you for your attention and ask you for questions. But before that, I have one last slide of acknowledgement. There are various peoples which I acknowledge. First of all, my co-authors, and then Darkstuhl seminar where this research emerged from, and other people.
Thanks a lot, Holger. Very interesting talk. I fully agree with you. A lot of research anticipated for us and for many of our colleagues. Some questions?
May I? Should I raise my hand?
Hi, Nikolai.
Yes, Nikolai. Yeah.
Hi, Helga. I was a little bit surprised that you never mentioned the consensus. I believe that in teams of autonomous systems, the problem should be very important.
Yes, yes, it's true. In
And it is very complicated. It is very time-consuming. Okay,
yeah,
please comment.
In the transport robots use case, I told you we have this auction-based mechanism, and of course there is the question of consensus. How do the robots, if it's completely distributed, how they agree on who got the job? Of course, the one with the highest bid, but of course there could be a tie break. If there are two robots with the same bid, there could also be disruptions in the communication, because the VLAN, the wireless network, is not very strong in these factories, so there could be loss of messages. So it's a technical problem on how do you make sure that only one robot gets the job done, or gets the appointment of the job. Yeah. So the bidding phase, you can tolerate that there are message lossing and so on. What we did is we came up with a two-phase protocol. One is the bidding, and then the next step is the consensus. And then there's also a third round, which validates the consensus, where you can go back and re-establish the whole. What we do not yet have is, what we were thinking about is whether jobs can be auctioned if a robot decides, well, I got this job, but now I have some higher earning job, so let me put it on stake again. You could imagine the whole system as with let's say taxi drivers. Each taxi driver wants to earn money, and so there are customers wanting to go from A to B, and then a taxi driver bids for the job, and he tries to form consensus with his other taxi drivers. And now, should you allow a taxi driver to re-auction a job? And usually you would not allow that, or I'm not sure whether it's allowed because it may be too complex for humans. But maybe in this system it could be done. We have not thought about that yet. We have not implemented that yet.
May I ask one more question?
Yes.
Yes, of course.
You just touch a little bit, but could you please elaborate a little bit in more details? What if some robots are faulty?
Yes.
Could you please elaborate a little bit?
So there are two types of problems which a robot could occur. One is it could be temporary or permanently stuck, and it could be that so it could be able to communicate that it has a problem, as in the centralized approach, or it could not be if it's like in a shade and cannot communicate anymore. And so what we do is, in the first case, of course, it can try to negotiate its own affairs. So if it has jobs which are not yet being auctioned, it can say, well, these jobs are void, and try to do with whatever you do. In the second case, it's much harder because it cannot even communicate. It's being more or less an obstacle for the others, and the others have to find out how to deal with this situation. And for the practical purposes, currently, we cannot handle that. So if a robot is out of order and it cannot communicate anymore,
the connection is lost again.
Sorry, can you hear me?
Yes, now I can.
So if a robot is out of order and it cannot communicate anymore, after a certain while, this will be detected because it does not give any live messages anymore. And then a human operator is being called. But of course, in the far future, this is not a possibility because there will be no human operator. So we need to think about some, let's say, repair robot or whatever. But currently, this is still science fiction.
Okay.
Thank you. Thank you.
Holger, my question about your experience in communication and cooperation with different specialists in this domain, because it's not only software engineers, not only software researchers, but a lot of people related with social problem, psychology problem, and so on. What about formal methods? Do they understand your models, your approach, and so on, or some problem in this way?
This is what I meant here with this part and all this, right? So how do we explain systems for regulators? How do we communicate with them? And how what are the regulatory challenges? How can they grapple with that? Agreement on what is ethical, right? How do we formalize that? What is ethical decision here? Yeah, and so a very practical problem. I told you about this factory, and the workers were standing there and smoking cigarettes, and the robot was just standing and waiting for them to go away. And then it was blinking, and they didn't go away. It was beeping, and they didn't go away. Should it, for example, approach them and sort of push them out of the way, or shouldn't it? Yeah. So as a human, of course, you would say go away, and then if you don't go away, you would go like, you know, very slowly approach them and put some pressure. But is that ethical or not?
Yeah, yeah. Okay, so we have to finish. Many thanks, and we are waiting you this autumn. I hope you could visit Moscow.
Okay. Yes. Thank you.
So,
thank you for the invitation.
Yeah. Bye.